Hello everyone, thank you for coming. And welcome our first talk from today, who will be working in the Department of Computer Science. And Dr. Zhuang Liu graduated from Tsinghua University Yale class in 2017 and later PhD at UC Berkeley. After he got his PhD degree in 2020 at Meta for 3 years. At that time, he worked with big shots in AI like Yan Lukun, Kai Minghe, and Zai Ningxie. And at the age of 30 years old, and he got cited over 80,000 times. So today he's gonna introduce his latest work on AI about data bias. So let's welcome him.
Thanks for the introduction. Today I will discuss a decade battle on data bias with the year. So before talking about data bias, again emphasize the importance of data in machine learning. So in machine learning, you can see that two components. One is data, another is model and optimization and other methods. Right. So I want to note that data actually defines the goals, while the model part is the means. We should not, with like over 95% papers on research papers on modeling and methods, we should not overlook the original goal we were pursuing, which is data. That is the XY mapping we are looking for a model to solve. For example, in medical diagnosis, the input is medical images, and output is, for example, diagnosis. In say text summarization, the input is a long text, output is a short text describing the main idea. So this input-output mapping relationships is what we want to learn. And now we have so much advanced AI, the difficulty becomes defining what problems defines general intelligence or super intelligence. You'll find the definition also resides on what kind of data relationships it want to model. We don't define super intelligence as what models we want to use. We define it as the data mapping we want to learn. That's again demonstrates the importance of data. And looking back since the deep learning revolution in 2012, I can roughly divide the forces of these two different eras. Since 2012, the AlexNet moment, all the way to 2018, where a lot of advancements are driven by new architecture innovations like residual networks, transformers, GPT, and mixture. Even mixture experts was invented at that time. Also, optimizer, we have our evergreen Adam optimizer, which is still used today. And since 2018, I can argue that the pushing forces of the field largely changed to data. First, we can data, right? Scaling, we have scaling compute. Scaling compute architecture, usually we don't do new architecture innovations, but scaling data, we really want to make good use of the internet data and curate them, filter them, so that we have high quality data that we really want to learn, like Wikipedia and Reddit. Then we also have a giant wave of training transformers on different problems. For example, vision transformers was invented in 2020, but it's an architecture work, but you can see it as just training transformers on a different type of data, which are images, right? And also with recent advancement in coding math, the training and the method largely the same. It's just the data we train it on is changed, and through just tweaking with data, we achieve so much progress. SFT and ILHF, which are post-training methods after pre-training data, we can also view them as training on different types of data. for SFT, supervised fine tuning, it's essentially creating a user assistant interaction data and still apply it to this kind of data. For reinforcement learning, with human feedback or with verified reward, they are both like training the GPT model but on model self-generated data. So all this you can view it as a unified framework of trying almost the same architecture on different types of data since 2018. And this is a recent blog by an author, Sebastian, about all these recent frontier labs architectures for their kind of flagship model. And you can see, as researcher in architecture, you can have a lot of technical discussions and differentiation between them. But first order observation is that all these architectures are very similar. They are all transformers. They all have most of them have mixture experts. They have self-attention, and they are not. So arguably, the models are more or less the same. But when you interact with them, you can still tell between them, and that difference in data. This release their data, and they have their own private kind of curation of data, and that is what was making the difference. Some models are considered here, some models are considered a bit lagging behind. And of course, the data progress didn't start in 2018. We can review the very history of dataset and going back all the way to this very historically important dataset called MNIST, set of grayscale digits. And you can see it's a very simple distribution, right? Just imagine small, tiny images with low resolution of digits, right? But if we apply our scaling philosophy back to the 2000, we would want to have more such digits, right? And you can scale even more. This is not a good way of scaling data, right? You can clearly tell why that's the case, because it's a too narrow distribution. It's only good as a machine learning. It's not really modeling in the real world. No matter how large model you train, how much data you have, you'll have a digit model at best, and that is not even good for colored digits. And then people, of course, they know this, and people are moving towards more like real world modeling dataset. And this one is another milestone that has been very popular for another long period called CIFAR-10. It now has 10 animals and vehicles, but still quite low resolution and only 60K data points. And then moving forward, we have a giant ImageNet. Now 14 million, and it has 1K categories. So you can see that it covers different things, objects, but still defined by a human curated taxonomy or hierarchy of concepts and categories. And then moving forward, we have this supposedly more comprehensive dataset called 5cc, which is another magnitude larger, 100M. It's all user uploaded images on the website called Flickr, and it's without. So that means any image can go in. So supposedly now it's even closer to the real world, right? You can see again, almost all things can be represented. And then comes the rise of image and also with corresponding datasets. Also, one of such category is conceptual captions, or CC, by Google. It's an image that's not just from one website, but from all of the internet. It's a difference is that just now image comes with a descriptive text. So you can see that now the will be included in the data is even more relaxed. It can just be any web image. So now we can see just more, even more representation of this commercial and digital graphics. And finally, we have this most recent one in our consideration data comp. Now we are finally at billion scale. It's a similar image text dataset with concept, just larger and it's from a giant web archive type called common crawl. So you can see from MNIST, we've really come a long way, and a lot of concepts that are not imaginable for MNIST are now all represented in this very giant comprehensive image datasets. And can we conclude that our dataset is already finally representing the world accurately? It's a tempting assumption to make given so much progress we've made. Now you think of a concept that's not included in this datasets. So we for the purpose of our experiment, we will hold this as an assumption we want to test. This is indeed a lot of assumptions to a lot of vision researchers, even to me and my collaborators, who worked really extensively with vision datasets. And we thought this new wave of datasets should really include everything. So here comes our first work in a series, who shares the same title as the talk. You'll see why it's we call it the decades battle on dataset bias later. So suppose now we have these three datasets, latest ones we just mentioned. If they are all really comprehensive and general, we should not be able to tell the clues from their images, like which dataset it is, right? So what we did is like we ran this experiment. We build we use a standard neural network model as a classification model. And now we want to task this model with this very contrived artificial task, which is given an image, can this classifier tell which dataset this image comes from? So no one would do this dataset unless like for your own fun. It's not a like serious task. It's definitely without much commercial usage. But it's a good test for the assumption. Like if all these datasets are already equal to the world, they should be like indistinguishable among themselves. And of course, we have our training and validation speeds, right? We don't want to have data leakages. So of course we have to test this classifier on a separate set that's not seen by the classifier during training. So if the assumption is correct, like if we already have our like holy grail word dataset, this can't do any better than random guessing, right? Because any image could be equally likely just from any dataset because it's just all the so-called word distribution, right? So we actually ran this experiment just with a standard classifier you can think of, ComNet or Vision Transformer. So anybody wants to take a guess on what the actual accuracy is? 40%. 40%. 80. You can only guess if you haven't read the text. Yeah, so the actual accuracy is very high. We are at 85% accuracy. So this also surprised us. So this means these datasets are still revised. So if we include another 3 datasets, including that, now the random guessing accuracy is even lower, 1 in 6, right? And the model accuracy is also lower, but that's because the task is harder. Still very higher, multiple times higher than chance accuracy. So this very simple experiment demonstrates that this seemingly presumably diverse datasets that are like in million, 100 million, billion scale datasets are still incredibly biased. Because they have clues that can be told from single image that tells you information about which dataset it is. And actually, this task doesn't require a lot of training images. So we only take a equally larger number of images from each dataset, and even with as few as 100 images, which is kind of totally unreasonable for typical image recognition or classification task. But on this task, can still do quite good at 61%. And of course, with the increase of more data, the tasks become easier because it's easier to find the patterns. But this also means that this task is not achieved through memorization, right? If you have more images, it will be harder to memorize. So it's not just memorizing individual images and finding duplicates in another split, but it's actually generalizing to learn a pattern. And to reduce to make sure we are not just like fooled by this result because of some other reasons. We do this corruption experiment, which is applying very heavy but equal corruptions to all the images in 3 data sets. So as to hope to suppress these low-level signals that could be unique to each data set. For example, they might have different JPEG compressions in their data creation process. We don't want the classifier to be only learning that. So we kind of use this corruption to heavily suppress such signals. And with this kind of images blurred to this degree, we can still get like 78% accuracy. Not such a huge loss. That means the signal is likely mostly in the low frequency semantics patterns. So what we did in this work is not new. It's a very interesting thought experiment, and actually it's been proposed more than a decade ago by this paper called Unbiased Look at Dataset Bias. But there were no such large-scale datasets. Datasets were quite specialized, and even human, when you present the images, could easily tell. A human expert in vision datasets could easily tell which dataset the image dates are from. You can see from these boxes, some of them quite specialized. Back then, they used the SVM classifier to do the same task, and they found that you can achieve 36 or some like near 36% accuracy for these 12-way classification tasks. So in a way, we didn't get much better in terms of building general purpose vision datasets since then. So after all this conclusion, so if datasets are biased in their own way, what would be an unbiased dataset look like? Is it a notion that we should pursue, we should define? Is there such thing as a word distribution? If we assume there is this kind of ground truth distribution we want to pursue to try a general purpose vision model, what does it look like? Some possible thoughts are like taking a random location on Earth and then taking a random camera angle and shot a picture, and this defines the distribution, right? But there are obvious problems with this because most of them will be in the ocean, and half of them will be at right. And also another way to define this would be from a human perspective. We can take a random human being on Earth and a random time snapshot through their lifetime, and then define what this person sees as, and randomly draw a picture image from what this person sees. And this is also comes with its own problems because now we don't have this monitoring cameras modeled in the distribution. It's all first-person egocentric images. So this is still an open question to me and to I think for other researchers as well. But at least in our existing datasets, we are very far from such a notion of a like real diverse and general purpose dataset. Conclude this work, we found through this very simple dataset classification experiment that modern large-scale vision datasets are still incredibly biased. So now we know these are 2 images from each dataset. We know they have contain clues, but where are the clues? How do the classification model know which dataset it is? Where are these signals embedded? Is it mostly in the semantics, or is it in a spatial structure, or even in the color distribution of these images from different datasets? So in our next work, we aim to update these factors and have a fuller picture of what caused this bias. So this work is understanding bias in large-scale visual datasets. It's actually published before our first work, what we do in this work is this: we do a set of image transformations to isolate certain parts of the images and keep the remaining parts. For example, in this one, we do a semantic segmentation transformation. We run a semantic segmentation model for each of the images and only keep the semantic maps. Now we only know kind of the object layout and what the object is, but without knowing the internal texture, the internal parts of the commonly defined objects like animals, right? So even with this, the human might experience a lot of signal loss by this, right? It's not as informational as the original pictures. But for a model, we do the same experiment of three-way classification. We still get 2/3 accuracy, which is like a decent drop from our 80-something accuracy, but still very much better than random guessing. And even this is also true if we just keep the caption. So here we run a captioning model, so that now each image turns into a text. There's no image as input to the classifier, only text to now a text classifier. And if we do short captions like this, we still get 60%. So that means a lot of the bias is indeed in the content they cover or the semantics. If we do longer captions, it's even slightly better at 66%. So all these two experiments mean that obviously semantic bias is an important component of dataset bias that contributes to the degree that the classifier can tell with 60-something% accuracy. And next we examine the structure or geometric features. So in this case, we run the segment anything model and only retain the edges. So edges, these are more fine-grained than the previous segmentation model, but they don't contain the object classes. We only have the edges. We fit these images to the same classifier, train again, test it again, we have 73% accuracy. So this is slightly higher than the semantic ones. So this means the geometry of the images contributes to an even larger degree. Same goes for the depth transformation. So these depth estimators run on the images, where darker colors means larger depths on the pixel. So obviously, shapes and geometry variations are significant between these datasets. And this is a kind of the more extreme version. We completely shuffle the pixels. So each image actually looks like Gaussian noise, but its original image is just with pixels shuffled. So even with this, so all the structure textures, the shapes are destroyed, but only with kind of this color and brightness represented, right? Now we have lower accuracy, but still quite better than random. And here we do this, but patchwork manner. Surprisingly, this almost keeps all the accuracy. We're still at above 80%. So only very local structures suffice to encode the bias. And this is the most extreme, where we reduce each image to a single pixel. So we just average out all the pixels, all the RGB channels, not channels, but we only keep one RGB value for each image. And just on this kind of the uniform images, we still get close to half accuracy. And here is an experiment on the inheritability of dataset bias through training generative models. So what we did for this one is we train a diffusion model on each dataset separately, and then we use this individual diffusion models to generate synthetic data set that is unique to each training dataset. And then we do classification on these synthetic images. We still get close to 80% accuracy in this case. That means these biases are largely inheritable. But the accuracy is reduced, which could possibly be because diffusion models have their own idiosyncratic behavior that they kind of reduce the bias the classifier can tell. So synthetic images can inherit the bias. So that was kind of the first half of this analysis. The second half is where we with the help of language and visual language models assistance, we directly ask these advanced models what the bias is at by providing the image and caption informations. So now we first we transform each image to a text for easier for more convenient analysis. And then we run a classic unsupervised topic discovery model, LDA. And we now have 5 topics. Each topic has 5 words representing a topic for each dataset. Now the picture is more clear. While CC have more outdoor scenes, and CC conceptual captions and DataComp have more digital graphics just from this objects feature. CC is kind of more like a blend of two, but you can see there's a spectrum. On the left is more natural scenes, natural images. On the right is more commercial and digital images. And we can, of course, we just feed the captions to LM and ask LM to summarize for us. Here's after some prompt tuning, we get this kind of more formatted results. But this is still too long for presentation, so I summarize even more briefly here. Clearly, we can see outdoor natural human-related things that users like to upload to websites. DataComp features more static objects, the most web-heavy, web-flavored dataset. CC is a blend of two, with both natural images and digital images. So for this work, we did a lot of indirect analysis by using transformations to isolate bias. And also, we can just directly use LM, feed the image, feed the captions, and ask it to summarize. We can see the result is quite informative. And that's the part for images. But now language models are really the AI we interact with the most, right? Ideally we want to know whether this language model from the bias problem with their different training data set. This is not doable because this companies that do not release pre-training data. So we in this work we use their outputs, this model outputs as the proxy of their training data, right? Because you can imagine the outputs largely determine what the inputs as training data. And of course, studies output bias or output differences between these models itself can be very useful, can provide perspective that are not obtainable from just seeing the benchmark numbers, which all of them are quite high and similar. So here comes this work that applies this data classification idea to language model outputs, where we call the bias now idiosyncrasies, because data describing the data, but describing the model behavior, the model outputs. So again, we still have our familiar, very simple artificial data classification framework, where now we feed the same prompt. We ask the model to do the same thing, but to different models, and model will behave differently. Some will be, they all have their own style, right? And what we do is, again, we train a neural network classifier to tell, now a text classifier, to tell, to do this 5-way classification task, to tell which use this text. And we use a function called LM to detect the input and produce the embedding, and then you can train a regression or linear classifier on top of the embedding. So it's all standard text classification. And here comes the results. Very direct. For each pair of the models, we achieve almost perfect accuracy. And this is also even true if we combine all of them together. 5-way classification, we have 97% accuracy. This is much higher than the pre-trained data sets. So this model outputs are really very, very different. And you can clearly tell which model it is by giving the text, as long as you reach this 5-class problem. And these are open weights models. And even on the base model, which through instruction tuning, can still do quite good. In base model, all the learning target is prediction. So they didn't go through different fine-tuning, different styles of fine-tuning, so that you can expect model develop different personalities. So this 7% accuracy largely come from different pre-trained data. And this is the input length you train with the. We can see even with one token, even we only fit the first word spit it out by each model, we can still get like 60% accuracy. That means the first word to tell in a lot of cases which model it is. And here is the distribution of the first word. If we count the, I guess the accuracy will be higher. You can see like they all start with the or here, right? And this, they have different preferences. And here are another way we obtain the so-called characteristic phrases. These are not the most frequent, but this provides the most clue that you can imagine the most frequent will be the, right? But the most characteristic phrases are the ones that are most used by this model, but not as often used by other models. You can see you wouldn't expect the defining features of these models until we do this analysis. And a similar analysis as a experiment where we now ask another model to the output, so that we hope it will suppress some style features or personality features. So we all fit these 5 model outputs to a single same model, and then ask the classifier to classify it. We can also do translation. So in this case, we did English to Chinese, and we can see these two in the same like text length. We still have above 90% accuracy. What's different is summarization. For summary, if you ask another model to summarize the text generated by these models, accuracy will be much lower. That means a lot of features, a lot of characteristics will be lost. So this could be to hide your identity. By summarizing, of course, reduce the length. And we feed these outputs to language models themselves to ask it to summarize the details, the features for us, right? In this case, we can differentiate between ChatGPT and Cloud. We can see ChatGPT has preference for more detailed and whereas Cloud produces more concise and direct responses. So this might be consistent daily experience. So also ChatGPT has more markdown, definitely the case. I think when we did this analysis, it's of this year, so it hasn't as much emojis. So to summarize for language part, we can see that language models outputs have similar idiosyncrasies as bias in vision data sets. So we can infer loosely that the training data is still also biased. That means even though we may be running out of internet data, these different models are clearly produced on different pre-trained data sets, different styles. So what are some places we can make progress regarding this data set bias problem? Is how to measure quality and diversity. So going back from MNIST all the way to our modern comprehensive datasets, we can clearly see that the first row is extremely low diversity, and with more recent datasets, we have higher and higher diversity. So there's no denying that we made a lot of progress. But how to quantitatively measure such diversity and quality, other than just we see it by our eyes? Is there a metric we can develop that is very correlated with human perception and correlated with the model's ability to generalize after training on this dataset? The diversity of datasets to train on it, which can be very time consuming and not good for iterative. And promising thing to do would be to develop a metric that can maybe run it one time and see of its quality and diversity. So how to create a truly more diverse datasets than this existing. So suppose we have a diversity metric, a quantitative diversity metric. Can we optimize it algorithmically, and go back to the old way, old ImageNet way of constructing the taxonomy? In that way, actually, we can make sure that nothing's left out, right? That's perhaps also one reason why ImageNet has and so persistent throughout the years. And finally, next, I want to talk about whether we can utilize synthetic data to remedy the lack of representations in these pre-training data sets. So image question answer problems that are easily answered by human, but very hard for all vision language models. And we found that it's largely due to the training distribution doesn't contain such things, such texts that are concerned about these questions in the image, so that we don't have a good model for these images right now. Can we post this with data by adding the data distribution of data that are lacking in training data? And can we close the synthetic to real gap? This might be one promising way to also address them. We should do open their release as much as possible. So in the beginning, is the crucial part. Architectures, they're more or less matured. So when we release the model, we should better release the data, which is the most important behavior determining part of the machine learning pipeline. Recent work that, of course, we should do this within the legal and respective framework. And finally, I want to thank my collaborators. Goya Minjie is from CMU and now working at Thinking Machine Labs. Zhiqiu Xu is a PhD student at UPenn, and Zico is professor here at Boston MIT. And to summarize what we found, scale alone does not solve data bias, and high quality, diverse, and well represented data sets still very much. That concludes my talk.
Classifier did you use to classify one response is generated by which LLM? Is it complicated or it's a big AI model? My question is actually, can you actually tell whether an article or a grant is written by AI or by a real human? Can you tell that?
I think there's a live work on that as well, but in this work we AI themselves. Yeah, kind of it's a continuation of our previous database work. We don't have a human there, and for the classifier we use this embedding model called LM2VEC. It's kind of the new state of the art for text classification. It's also based on LM. Just use LM's embedding, and then fine tune it to with the softmax regression to determine which dataset which are generate this text.
Have you tried to detect whether it's human written or machine written?
We haven't in this work. I our work that yes.
I think most people would assume those large language models are trained with the same data. But you still see, even for the base model, they're largely trained by next tokens. But why? Like,
I think that's the secret we don't know as an outsiders, right? I think companies what determines the quality of their internal emphasis and the abilities to data. I think some labs are just better and earlier started doing this earlier than others.
probably also use different data cleaning criteria, so that causes the data distribution.
I think there's a lot of knowledge there, ad hoc knowledge.
So the first one just is but I mean you just using the output, right, and the prediction, train a model and do prediction, distinguish the source, right, from the different L. I'm thinking even you have this 99% accuracy to distinguish different source, can you tell that's because of the training data or because of the infrastructure? Even such as maybe you have you probably add another. We have a same train data set for train different kinds of.
Good experiment. We should have run. I actually another audience member gave like experiment like giving fix the data, train different architectures and maybe hyperparameters, see how much the output is different. I think that's very important, and I predict that will actually validate my point that hyperparameter and architecture define much less the behavior than data.
Because now the experience just can tell that they are come from different source, different kind of LLM, right?
Yes.
We cannot that. Another thing is that even you have the same infrastructure, totally always the same hidden parameter, the hyperparameter, all the same parameter. If you also have the same data, but you have a different kind of order of data, will that also affect the training state? Because if you have different random throughout the data input, and output of the after training have different parameters, maybe the follow-up classifier can also distinguish kind of difference. Then maybe the difference not always come from the data itself, because those kind of LM is too sensitive. So another
perspective, the database, I think the market is just really telling the idiosyncrasy of the outputs.
Yeah. It's a question about, because you talk about the world distribution, right? So you just have this kind of the Earth picture, the world distribution, right? So I'm thinking in the text, do you think that kind of world distribution for the text? I mean, if we regard those kind of different kind of data set, we call the bias, right? Is that kind of really just a perfect way to get a unbiased data, text or image? Can we really reach to that point or not?
Yeah. How to lean into say you want super intelligence, that's really good. It's not you wouldn't ask it to do like daily stuff, right? You want a general purpose model and a super capable model on certain tasks.
Yeah.
Maybe the general purpose model, maybe we'll converge to that. I think we might have a better chance because we we collect all this ChatGPT user data and collect. They'll have a good model of what wants or wants to interact, and they might at least like a general purpose assistant models prefer this data distribution. Maybe that is more realistic.
That's very interesting. Thank you very much.
Can I ask a question about intellectual property? So for example, I'm sure you're aware, like the NIH, for example, does not allow reviewers to use ELM based approach, for example, to create summaries of grants or anything along those lines. So the concern obviously is that you are now uploading unpublished data or ideas, to a modeling system. Do you think that concern is overblown? Is there a way to protect that somehow?
Turn off the history function.
I see.
Okay. At least I don't know. Maybe the best practice, of course, follow the policy, right?
Right.
But I see. Yeah, actually, there was a tweet on Twitter circulating that use it for them. Actually, they might leak. They might be searchable on Google and something like that.
Precisely. And then someone else could actually ask that question, and
Yeah.
then now you've provided a solution to something that hasn't been published yet, or funded yet.
I think the least we can do is to really turn off the history and
I see.
right, yeah.
I see. So by turning off the history, you don't allow it to use
No.
that data.
So last time I checked.
Excellent. Thank you.
Question chat. What kind of model was used? We most of experiments, and we also did different models, and they all performed more or less E2 to 85 range. No matter you use ResNet, Connext, VGG actually, very old one. Only if you use AlexNet, you'll get slightly lower, like 5% lower.
Some question. I think so, because you claim that the data is bad data, but for example, every person you can just see some part of the data in the world. For example, you and me from area, we know a lot from the data from Asian area, but some guys came from the USA or European countries. So the question is it is very, very important, or something like the impact will be have in the future models or something like that. It could, yes, something like that.
You mean the rough
Yes.
of each dataset?
Yes.
Yes. I think that no one. There are other very notable works on focusing on geographic bias, and they have mitigation methods that let you. I think the most direct approach is to collect data set that fairly represents regions of the world. But other than that, there are also adaptation methods that let you better transfer your model from say a Western region to a developing region.
I have a question. If data bias about using synthetic data, all those language model companies, they heavily use synthetic data for training. That is mitigate the problem of bias. This is the first question. And second question is, the digital data is just growing like very rapidly. Do you think it will outgrow like the GPU's power over time at some point? Even you have that data, you don't have the computing power to really leverage the data.
Yeah, the first one, synthetic one, data definitely have their own bias. Actually, I find a lot of image generated models generate images that are too like artistic, not realistic. And if you train on these artistic images and then generate synthetic images, it will be even more artistic, and then you kind of in this loop, right? It will be worse and worse. I think, yeah. When synthetic data doesn't work, you don't know whether it's because synthetic quality is not good, like the semantic quality is not, or because the synthetic has its own bias, right? So actually, one of the projects we are investigating this problem. We find some synthetic data are not effective in mitigating these vision language model errors, and currently we are still exploring whether it's because of synthetic real gap or because the model just didn't learn as well. And the second question is whether data outgrows compute. For vision, I think that data is always like out of bound for compute. We're still struggling to produce to train non-video models. So I think like each day we receive like much more vision piece of information than we speak out words, right? Or we read text. I think that's always been a problem for vision. So even this existing long video data is challenging for us. If we include the glasses now, like data classes collected by glasses, like this everybody's egocentric data, it will be huge and vastly outnumber YouTube's existing data pool. And I do think this data outgrowing compute problem is always true for vision. For language, I think it might be less severe because they're talking about they're running out of data on the internet. So I haven't trained language models, so I couldn't speak too much. But I heard that they only train for one epoch now. So presumably, like now we are in a good, like balanced place of like we can data without repeating them while I think the growing speed of data is actually may not be outpacing the model scaling in recent years. So yeah, that's my.
Can I? Thanks for the great talk. My question is does the bias affect your training? So if we devise the data set, does it contribute to the enhancement of the model performance?
It's very hard to debias. One way to debias we considered is to kind of zero training, right? Data, so that the classifier cannot tell which data set this comes from. This ends up only adding these observations like adversarial attack signals onto the images. That you don't see any style change of the image. So and the image becomes like with more artifacts, and it's not good devising method. I don't know what a good devising approach will be, and whether it's possible to devise rather than just recollecting the data. Yeah.
The image, let's say you have sets. You pre-train your model all 3 data sets, and then do an experiment where you take 2 separate data sets, not be previously seen, give a pair of images and ask them to say whether they're from the same data set or from a different data set. So it's like a separate experiment. Would training on multiple data sets reduce, and then the performance, do you think, will be close to 50% in that?
Yeah, we haven't tried that. I think it may or it may not. But one thing we found is like if we pre-train a user unlabeled model on unlabeled data, and if we only use the features with frozen weights, these features alone can be good to tell to do this there's a classification features is already enough. Like maybe not to the same degree if you just train this on the same task, but it's general patterns used for image recognition. We find them are also useful for data classification.
Is bias really a bad thing?
Yeah.
We see that all the LLM a different loss. So everyone wants to have their own style. So you don't want to train some artists, they produce exactly the same work.
Yeah. True. I think it's as a field we are moving toward models. That's a trend. Whether we want to go to the very extreme of this trend, that is questionable. Before like large language models, we have text summarization models, we have like sentiment classification model. Now it's all just been ChatGPT. I think that's a very good progress. But whether I think we want general purpose, yes, and then it's like human, right? Humans they have a good model of what a good life could be, but then each person has a different interest or different career, right? So I think at some point we have to strike balances.
Could I have so I have a small question about the bias among the images data sets. So that do we have the baseline test like we mess up all these data sets to see the accuracy? Because for now we just assume that the accuracy is 30%, but this is the most ideal situation, right? The real accuracy might be affected by like the size of the different data sets or the classified itself, right?
What?
I mean, the baseline test, we just mess up all these three data sets.
Yeah, a single data set split it 3 ways, right? That would be a baseline, the same baseline you mentioned. You can mix the 3, but you can also just take 1 and then split it 3 ways, right? And then do a classification among 3 ways, three subsets, if you will. And then its accuracy is random. It's around because set active. It's an impossible task, and indeed we did do that. It's the same with data sets first. It's called the combined data set, single data set again, right?
Can I ask a question? Yeah. So regarding LLM, you told that Rise tried to detect on the summary of the outputs, then you found that the bias was quite little compared to when the exact response was fed to the models. So can you say that because you summarized it, the knowledge remained same, but the choice of words were removed, and the choice of words are mostly because of the fine tuning part where you train a base model to behave more like a chatbot, so it can be that part of training that introduces the largest amount of bias.
Yes, I think that's probably what was, and also we have phrasing removed a lot of word choices. Actually, we have another calling the words. You take all the punctuations and special characters. You just make it a bag of words and shuffle it, and on this we can still do 90% something accuracy. And paraphrasing. Still keeps at 90, but summarizing keeps reduces down to 50 something. Is the most yeah.
Yeah, thanks. Thanks for your talk. Actually, I have a question concerning. I noticed in your first part you're trying to analyze the bias of different data sets. As the last area, try to summarize the characteristics of different data sets. So we all know that each data set is very large, so how you can take the whole data set?
We only take a sample.
You take a subsample.
100. Once we probably only take 100 to 300 ones from each data set. For the classification, we take either 1M images or 100K. So very tiny subset of them. 0.1% if the original data set is like 1B or 100K. Not a difficult that requires using the full set, only a very small sample.
Okay, yeah. And another question will be like, in the second part of your talk, you talk about like the different LLM will have the different capability concerning different prompt. So how do you make sure that the M you use to summarize the data set doesn't have certain bias to certain data set?
Yeah, yes. So whenever we use the model to analyze other models, we cannot, we face a problem of introducing bias through that model. So I think that's just, you try different models to summarize the results are kind of more or less similar. Yeah.
Thanks. So as to the last part of your future work, you talk about how to use different metrics to measure the diversity of the data set. So would that be finally we are going to use a bunch of the different model to measure the subset of the data set and to give a summary of all the answers given by different LLMs?
Yeah, I thought of diversity measuring more as a number. So it's a like single number, which higher means higher diversity, lower means lower diversity. What
When
we
you measure the diversity, would it be measured from the different perspective? Because your first part of your talk, you talk about you measure the diversity of the data set, of the vision data set from different perspective, like the semantics, the depth, or the color, or like the even the geographic. So yeah, with that, finally the diversity will be like a list of the number. It will measure the diversity from different perspective.
yes. Yeah, I think will be mostly will still be a single number, but that can be like different subcategories. Just like people when they refer to benchmarks, they report the average performance, right? So yeah, still hard to say which parts we should weight, how we should weight different parts, because some you can imagine some aspects matter more for training, for learning, and some aspects matter that. We don't have a good solution. Why? That's why it's an outlook. Yeah, outlook.
Yeah, thanks.
I think we should thank you very much for a great talk.
Thank you.